So yesterday I tried to explain the relation between excursions and trading strategies, and we defined the notion of delta excursion, and we showed that how the decomposition of a signal into delta excursions leads to a natural representation of the trading strategies associated with that signal, and we showed that it leads to simple expressions for um, like the profit, the risk, and maximum loss drawdown of trading frequency of these strategies. So here is an example. We looked at the trading strategy, which consists in shorting a portfolio when the signal goes above some threshold. And then we show that it can be represented through some sequence of stopping times, the level crossing times of the threshold and zero. And then if we have the decomposition of the signal into delta excursions, which is shown here, then from this decomposition, it's very easy to compute things like the frequency of transactions, realized profit, the gain, the maximum loss, the drawdown, and so on. So one of the questions in the design of these mean reversion strategies is how do you choose the threshold delta? And especially in intraday trading, most of these strategies involve intraday trading. You can choose very small threshold delta, which correspond to very frequent trading. So one question we're going to look at today is how do these quantities behave as delta goes to zero? And we will see that the answer depends strongly on the roughness of the signal. And in fact, we're going to establish quantitative relations between these quantities and the roughness of the signal, which we will define in a very careful way. So that's going to be the focus of today. So we're going to now look at, so what I did yesterday was for general paths. I didn't specify any property of the path except for continuity. And but as you know, if you look at signals in finance, they're mostly irregular as a function of time, in fact, very irregular. So we want to see now what's the consequence of this irregularity. And we see that this is actually very important for the study of these quantities when delta goes to zero. So if you have a smooth path, say a differentiable path, then the level crossings of this path for any two level zero delta will be finite over any finite interval and discrete. So you can, they're well separated because of the smoothness, you can extrapolate the trend, so you can forecast the system over a short interval. And the level crossings will be discrete, they're well separated. However, if the path is very regular, like a diffusion process, for example, or even worse, then funny things can happen, and the signal can cross zero, for example, infinitely many times over a finite interval. So we will see that. And for example, this is the case for Brownian motion. The behavior of Brownian motion at zero is well studied. The zero crossings of Brownian motion are captured in the concept of local time. You may be familiar with this. And the concept of local time is necessary because Brownian motion can, actually hang around zero many times. It can oscillate around zero and accumulate a positive occupation time at zero. So for paths like that, when we look at the behavior of these level crossings when the level goes to zero, well, the number of level crossings will increase when you decrease the level to zero. And if you look at how we define the strategies, we trade every time we cross the level delta. So this will lead to more transactions. So this will lead to the high frequency asymptotics of the strategy, high frequency trading. But each time you trade, you remember that each time we trade, we earn delta. So we have more transactions, but a lower profit per transaction. So it's not clear whether that's a good thing or a bad thing, because on one hand, you have more transactions, but then you have a lower profit per transaction. So it is not obvious which effect is going to win or dominate as delta goes to zero. So in fact, we're going to see that it depends on the roughness of the path. In some cases, the interest of the investor is to have a low delta, high frequency of transaction. In other cases, there is an optimal delta, which is strictly positive, and so on. And we will show now that this trade-off depends on how frequently the signal crosses zero, and this is linked to the mathematical concept of occupation density and local time at zero of the signal. So this is going to lead us to some interesting mathematical considerations in this talk. Okay, so let's define what the quantities that we'll be interested in, and then I'll show how they're linked to crossing level crossings and how they are linked to the number of transactions and expected profit of these strategies we consider. So everything I say in this talk, like yesterday, is purely pathwise. There is no probabilistic assumption on anything. We're going to look at the path of a signal, and we're going to calculate some things for the path. So of course, we can apply this. We will apply this at the end to paths of certain stochastic processes, but you can do this with one path, and it makes sense. So I take this path S, so S is the path of a signal. We only assume it's continuous, but all these things make sense for Cadillac, but I'm going to assume it's continuous. So S is some continuous function of time. And I define the occupation measure of this function S. So what is the occupation of the measure? It's a measure defined on the real line. So if you give me a subset, a measurable subset A, the measured megamity of A is simply the time from 0 to t during which my path spends, the time my path spends in A during the interval 0 t. So this is the occupation measure on 0 capital T. Okay, so I just integrate the indicator from 0 to t. This tells me how much time I've spent in the set A, how much time this path has spent in the set A. Okay, so this is a measure. It satisfies all the properties of a measure. So it's a measure on the real line. If it has a density, LT, we will call this the occupation density of the path. Okay, so the density will be a function of x. So the value of the density as x is called the occupation density of the path, LTSX. And as usual, you can think of the density as a limit. It's the limit of the occupation, the measure of a small interval around x when you shrink the interval to 0. Okay, so that's what we call the occupation density of a path at a point x. Okay, so what does that mean? Well, again, if S is a smooth path, this is 0. So there's no occupation density because typically a smooth path will cross x a finite number of times. And as you shrink epsilon to 0, this thing will go to 0. So the occupation, the measure has a density really if the path crosses x infinitely many times and comes back to x all the time. So really, so having a non-zero occupation density means that the path is very irregular around x. It's going to have a very irregular behavior around x. Now, this is the density of the occupation but measure. So it's you can characterize it as any density in terms of its property that if you integrate the density with respect to any measurable function, say a continuous function, then you get back the integral with respect to the occupation measure. So this is called the occupation time formula. It's really the equivalent to the definition. Okay, and so you should interpret this occupation density as the time S spends at level X during 0t, whereas the occupation measure tells you the time spent inside the set A. This is the time spent, at a small interval around X, if you want, during 0t. Okay, so why do we care about this? Well, you can guess why we care about this, because we're interested, if when delta shrinks to 0, we're going to be interested in the time the signal spends between 0 and delta, or outside this interval or inside this interval. And as delta shrinks to 0, this will be very well approximated by something like an occupation density. So you can see why we're going to see that. Okay, so as I said, we're particularly interested in the occupation density of our signal at level 0, not just any level, but 0. So we're going to use a special notation for 0, because we don't really care about other levels in this application. We only care about 0. So I will call LT of S the occupation density of S at 0. So it tells you how much time it spends at 0. So now, up to now, I fixed t. So I looked at how much time the signal spends at 0 or at some level on 0t. But of course, if you increase t, you're going to spend more time over the interval if the interval is longer. So it's clear from the definition that the map. So this occupation density LTS is increasing in t. So like any increasing function, it has a right continuous inverse, which we can define in this way. So it's the inverse of any increasing function can be defined as the infimum of the argument. In this case, it's a time value. It's the first time at which the occupation density exceeds some level lambda. I call this tau lambda. So this quantity is sometimes called the inverse low local time at 0. And it is really the first time at which the occupation density at 0 reaches lambda. So remember, if we wait, the more we wait, the more you can go through 0. And every time you go through 0, you increment LT of S, the occupation density 0. So tau lambda is the first time at which this occupation density reaches lambda. Okay. So tau lambda is also an increasing function of lambda. And it has some interesting properties. So the property, well, now, so what's the link with excursions? Well, you can see now what's going on, because LT, the occupation density, it only increases when you occupy 0, when you hit 0. So it increases on the set of times when you are at 0. When you're spending time at 0, you increase LT. But it doesn't increase outside this set. So if you look at any excursion going away from 0, until it comes back to 0, LT doesn't increase. So it means that LT is constant along any excursion going away from 0. So now, so it means that LT is going to be piecewise constant. It's going to be piecewise constant and along the excursions which go away from 0. Exactly. So this is nice because we can use this occupation density as a way of indexing the excursions, because each excursion has a constant value of LT. Now its inverse, tau, this function tau lambda, which its inverse of L, so the inverse of a piecewise constant function, if you have a piecewise constant function, if you want to invert it, you just flip the x and the y axis. So you can see that if the function is piecewise constant, then its inverse is going to have jumps. So the horizontal pieces of L become vertical jumps of tau. So the discontinuities of tau correspond to the constant plateaus of L, which are the excursions of S away from zero. Okay, so and the jump intervals of tau. So so therefore they are the complement of the set where S visits zero. So these are the excursions. Okay, so if you look at the jumps of tau, so if L is some point in the argument, tau L minus tau L is the interval describing the jump of tau at point L. This is exactly one excursion, and if you take the union of these, you get all the points during which S is not at zero, and each of them belongs to an excursion, and these excursions are exactly the jump intervals of tau. So this means that this occupation density and its inverse, what we call the inverse local time at zero tau, they give you a way of labeling the excursions of S. And so along each excursion of S, LT is constant, so the occupation density is constant, and each excursion of S corresponds exactly to one jump of tau. So this is a nice way to encode everything. And this was first noticed by Paul Levy in a study of the excursions of Brownian motion. Okay, so what does that mean? It means that, well, we can now use this occupation density at zero to label the excursions of our irregular signal. Why do we need this? Because you see, if when what we did yesterday, we had a finite number of delta excursions or countable number of delta excursions, so we could label them 1, 2, 3, 4, n. But if you have an irregular path which can go through zero infinitely many times in a finite interval, then the excursions may or may not be countable. So we can't just label them in order of arrival because we will run out of indices. So because it may be non-countable, it's a non-trivial thing to actually figure out the correct way to label the excursion. So that's why this idea of Levy and then Ito to label the excursions with this occupation density at zero is a really nice idea, because as you will see, it enables us to define a process which will be the collection of all these excursions, but there's no natural way to label them except through this occupation density, which gives a natural order in the excursions. Okay, so as we said, along each excursion from 0 to 0, the occupation density is constant. So, so it means that each excursion can be associated with a level of occupation density, lambda, let's say. And so we can define such a thing as the excursion of S with along which the occupation density is lambda, and we will call this E lambda. And what is this? Well, it's just a piece of S. It starts at the beginning of the excursion and it ends when it reaches back to zero. So it's just S, but starting from the beginning of this excursion and ending when the excursion ends. And when does the excursion start? When does it end? Well, we said that the excursions, the time interval of the excursions coincide exactly with the jump intervals of tau. So they start at the jump point of tau, and they end when the jump ends. So this is the way to define the excursion along which the occupation density is lambda. This is exactly it. Now, the only thing that can happen with the irregular path is that you can have these funny infinitesimal excursions. So think of a Brownian function. It can oscillate around the zero. It can wiggle around the zero, but not go away from zero. So during this time, the occupation density increases, and it's going to be it's not going to be a real excursion because it's not going to go away from zero. So in this case, tau doesn't have a jump because you are increasing the occupation density. It's not flat, so tau is not discontinuous. So it means that there are two kinds of ways to visit zero. Either you stay around the zero and you accumulate occupation time. So in this case, tau is not discontinuous, and we call these things infinitesimal excursions. But for our purpose, we're not interested in those, because if it stays around zero and does infinitesimal excursions, it doesn't reach any level delta. So we don't care about these. So we will put them in a cemetery. We kill all these excursions and dump them in a cemetery. So we're not interested in these. We're only interested in, finite excursions which go away from zero, really. And so we're only interested in those, and those correspond to discontinuities of this inverse local time tau. Okay, so are there any questions about this? This is non-trivial if you've never seen it, but it's super important because I'm going to use this all the time. So if there is any question about this, please ask. Okay, so this funny notation is, I'm trying to convince you that it's a natural way to label excursions. Okay, and because this occupation density is constant along excursions, so each excursion has a well-defined value of occupation density. Okay, now, so it means that you start with, at time zero, your occupation density starts at zero, and then every time you cross the zero, you increment it, and along each of these excursions, so go from zero to zero, and then again away from zero back to zero, the occupation density has a different value along each excursion, and you label E lambda the excursion along which the occupation density has value lambda. But as the occupation density is increasing, when you go forward in time, you can also, you use this as a kind of artificial time index. And for example, you can say, well, how many excursions, what is the number of excursions of a certain type? For example, how many excursions, let's say gamma is some set. So let's say, for example, gamma is the excursions which reach level 1 or delta, whatever. Then you can say how many excursions have reached level 1 up to now. You count them. But if you understood what I've been saying, the natural way to say up to now is really up to occupation density L, because the time is not the variable I'm using here. It's really the occupation density. Of course, you can go back and forth between regular time and occupation densities through this tau of lambda. Okay. So, following this idea, Ito in 73, he said, well, in fact, this is the most natural way to describe the excursions of a path. And so he gave the following description, and I will come back to this tomorrow because this is really a very important topic. He said, well, if you give me a path S, well, I can do like we said here, we can index the excursions of the path from 0 through the value lambda of the occupation density on each excursion. So we have an increasing set of indices, lambda. And then I can count for each level L, for each occupation density level L, and each set of excursions gamma. So the gamma is a set of excursions, paths in the space of excursions. I can count the number of excursions encountered up to occupation time L. So number of excursions of type gamma. Okay. And this defines a counting process. Okay. It counts the number of excursions of a certain type, type meaning a subset of the space of excursions. And Ito called this the point process of excursions, or the excursion process associated to S. So remember, S is a continuous path. And so in this way, Ito associates to any continuous path a counting process, so a purely a discontinuous object, which counts where do the excursions of S fall in the infinite dimensional space of excursions E. And so this object, this counting measure, contains all information about the excursions of S from 0, because it tells you when the excursions happen and what type they are, how far they go away from 0, what do they do, because you can choose any set gamma here, which has different properties, and you can say if there are any excursions of type gamma between this time and that time. But note that this point process, this counting process, is not indexed by time, but by the occupation density of S, because that's the natural coordinate when you move along S. Okay. So we're gonna just, so this, remember this counting process, the point process of excursions, this contains all the information on the excursion. We will see this again tomorrow. But for now, it's just a way to count the excursions which fall in a certain set gamma. Okay, so you will say, okay, what's the relation between this and the delta excursions we saw yesterday? Well, so here's the relation between these two things. So so now we're going to assume that S is not just a continuous path, but a continuous path which is sufficiently irregular to have an occupation density at 0. And the inverse of this occupation density, we call it tau, just as I defined earlier. And now we revisit our old friend, the number of delta excursions between 0 and t, d delta t. So what's the relation? Is there a relation between d delta t and this point process of excursions n, which counts how many excursions you have from 0 to 0. Here there's no delta. It doesn't care about delta. If you go from 0 to 0 just by having a small movement and you don't reach delta, this point process does count that. But so in this point process, you can choose any set gamma. You choose a set gamma of excursions and you count how many excursions up to occupation time L fall in the set gamma. And of course, there's one set gamma, which is interesting here, which is the excursions from 0 to 0 who reach delta. So whose max height is bigger than delta. Okay, well, then the statement is that, well, this set, if you plug this set into this counting process, then you get something which is going to be related to the delta excursion. So the statement is this. First of all, if the path has occupation intensity at 0, then for any strictly positive delta, if you plug in this set gamma delta into the point process, so if you count the number of excursions from 0 to 0 of your path which reach delta, this is going to be always finite. So this is a kind of a reformulation of the property we saw yesterday. You cannot have infinitely many excursions which cross a finite level delta, because otherwise the path cannot be continuous. So this is not new. But this is more interesting. The second line is more interesting. It relates the number of delta excursions with this point process here, n. And so it says that basically the number of delta excursions on 0t, which is what we're interested in, is exactly this point process. So you count the number of excursions from 0 to 0 which cross delta, but not up to time t, but up to occupation density LTRS. So there's a time change involved here. So it means that these two objects are the same, counting the same thing, but this one is in real time. This one is formulated in the time variable, which is not real time, it's the occupation density. So you need to compute it not at t, but at LTRS, the occupation density of the path at time t. Up to this time change, they're the same thing. And if you do the inverse time change, well, the inverse of LT is tau. So you can write the same relation in another way, which is that the number of delta excursions up to not time t, but time tau lambda being the inverse of the inverse local time. This is equal to what we defined as the occupation per measure, the excursion per measure at local time lambda. Okay, so this is so this means one is the time change of the other. Okay, and so how do you prove this? I'm not going to show the proof, but the proof is based on what we showed yesterday, the last exit decomposition. Okay, so why? Because what we showed yesterday is that if you look at the excursions from 0 to 0, well, an excursion from 0 to 0 can go through delta or not go through delta. And on the other hand, the delta excursion can go through 0 infinitely many times. So these two things are not related in a clear way. But what we showed is that any delta excursion has a unique decomposition into something that doesn't reach delta and a excursion from 0 to 0 which reaches delta exactly once. Okay, so it means that, so because of this last exit decomposition, it means that inside each delta excursion, there is one and only one excursion from 0 to 0, which reaches delta. And this is exactly the set gamma delta we define here. So it means there's a one-to-one correspondence between gamma delta, so excursions from 0 to 0, which reach delta, and what we call delta excursions. So because of this one-to-one correspondence, it means counting delta excursions, which is what d delta t does, or counting excursions from 0 to 0, which are in gamma delta, is the same thing because of this one-to-one correspondence. So this last exit decomposition is what makes this work. Now, at this point, you might say, okay, why are we doing this? It's easier to count delta excursion than to build this point process and local time. Why do we need this? Well, we will see tomorrow why this is interesting, because the entire theory of excursions built upon Ito's work, has studied this object N. And on the other hand, we know a lot about the occupation densities of stochastic processes, this LT. So if we put these two ingredients together, this will give us information on what we want, which is the delta T, the number of delta excursions. So this will be tomorrow. But I wanted to show this today because, as you can see, these statements have strictly no probabilistic assumption. They make sense for one path, and in the classical theory of excursions, they have been done for Markov processes, but they make perfect sense for a single path. And I wanted to show you the pathwise statements because they're really, they don't depend on any assumption. So that's why I make this statement like this today. This is not the classical way of presenting things, because usually they're presented in the case of a stochastic process. Okay, so this was a parenthesis. So what we really want to do is to analyze, as I said, the behavior of these properties of the training strategy when delta goes to 0. And now we're going to show that, this is linked to the behavior at the 0 of the path, the roughness, and so on. So how do we measure roughness of a path? Well, one classical way to measure the roughness of a path is to look at the sum of its increments to some power p, and see whether when over some time partition, for example, I'm going to use this partition. You look at this called the Lebesgue partition associated with S. So you look at a sequence of hitting times of levels whose distance is 2 to the minus n, and you take the increments along this partition, but we can choose another partition whose step goes to 0, uniform partition otherwise. So you take the sum of increments to the power p and along this partition, and you say that S has pth order variation along this partition if this sum converges to a non-zero limit as n goes to infinity, as you refine the partition. Now, it turns out that this sum either goes to infinity or to 0 or has a finite limit. There are only 3 possibilities. And there is at most one value, p, for which the limit is neither 0 nor infinity. So this value p, if it exists, it may not exist, but if it does exist, we will call this the roughness index of S. Okay, so very roughly, you can think of p as 1 over the Hölder exponent of S, but that's not exactly true. But let's say it's the upper whole Hölder exponent of S. But so this is the precise definition. So you look at this sum of increments of power p along this partition, and if it converges, then you say it has finite p order variation, but typically it will converge to 0 except for one value p, and that's what we want to estimate. This will be called the roughness index of S. So you may know probably that for Brownian motion and semi-martingales, p equal to works. This will give you the quadratic variation of the process, and so this is a well-known property of semi-martingales. So this means that in the terms that we define, the roughness index for Brownian motion and for semi-martingales is 2. But we will show examples of processes, and this is well known to people who have been doing rough volatility models and so on, that you can have financial signals for which p is different from 2. So the higher the p, the rougher the signal. Okay. And we're going to define a notion, a concept called local time of order P, which will try to quantify the irregularity of such a rough function near a level x. Okay, so to motivate this, so this notion of local time, I could just give you the definition, but I want to spend 2 slides on the motivation where this formula comes from, because I think it's important. So this formula I'm going to show you comes from change of variable formulas of like the Ito formula. So in a recent work with Perkovsky, we defined a higher order change of variable formula, which extends the Ito formula to rough functions of this type. And the idea, just like in the proof of the Ito formula, is to do a Taylor expansion of the increments of a function computed along the path. So let me just show you where this formula comes from. So forget paths and rough signals and so on. Let's take a smooth function f, which is Cp minus 2, so continuously differentiable of order p minus 2, and whose p minus second derivative is absolutely continuous. Then, well, we can write a Taylor expansion, a Taylor formula up to order p minus 2, and the remainder, I write it in integral form. Okay, so this is the integral form of the remainder in the Taylor formula. So this is a classical Taylor formula. Now, so the last term here involves the p minus 1 derivative. So if this p minus 1 derivative is of bounded variation, then I can do integration by parts here in the last term. So I can rewrite the last term in this form. Okay, so I integrate this, and I differentiate that one. So I get here, so I integrate the b minus x to the p minus 2, and I differentiate this p minus 1 derivative, so I get this form here. Okay, so if I plug this remainder into my previous formula, it shows me that I can write the increment of f between 2 points as, well, now I go to order. So now I add one more term here, this last term here, p minus 1 term. And then the last term, I can write this, so I can either do this b minus a or a minus b, so I can write this as sine of b minus a, but depending on whether b is greater than a or smaller. So this is just a change of sign in the integral here. And then the last term is this, the form here, okay? But I can also absorb the sign inside and write this in this form, okay? So I can write this last term as, so this last term is an integral from a to b. So I can write the last term as an integral over the real line of indicator of this interval times, now I put the sign inside to the power p, and now I have the absolute value here. Of course, this makes sense only for integer p, this sign thing to the power p, but I can make sense of it for an integer, and then you use the same expression for any p. So this shows that you can write the Taylor formula to order p minus 1 with this remainder term. And the remainder term involves two things, as you can see. You integrate along the function. What? Well, indicator of this interval times b minus x, so the one end of the interval minus x to the power, absolute value to the power p minus 1. Okay. So this motivates the following definition. I'm going to take the form of the remainder here, and I'm going to define a measure, a discrete measure, such that if I integrate the function with respect to it, I'm going to get exactly this term. Okay, so just this is an integral on R. I'm going to write a discrete measure such that if I integrate with respect to the pump function, I'm going to get exactly this integral term. And I'm going to, so this is the discrete measure. So I use this partition, and now A and B are going to be the values of S at points of this partition. And so the indicator of AB is going to be indicator of these two values along the grid. And I'm going to, I have this term, the value minus x, the value endpoint B minus x to the power p minus 1. So I'm going to define this sequence of functions. And this, if I integrate this with respect to f, I get exactly the remainder term. So that's the only reason I define it. Okay, so what if this sequence of functions computed along the grid, so now we're going to refine the grid. If this sequence converges, so it can converge in different ways. So here we're going to look at the convergence in some LQ. Think of it as L2 to simplify if you want, but we're going to use the different P's. So it's important to have the different notions of convergence. So if this sequence of functions converges to a limit, we call this limit L T pi P. And so the P is the same as here. We use the power P minus 1 in the definition. And we will call this limit the local time of order P of the path S computed along this partition, this sequence of partition. Okay, so the interpretation that I will try to justify is that this limit L pi P is the rate at which S, the path S accumulates Pth order variation at X. When it's close to X, and close meaning inside some interval defined by the partition around X. Okay, so this looks very strange. This definition looks, if you haven't seen it before, it looks a bit complicated. But what I try to explain is where this comes from. It comes from really the remainder in a Taylor formula. And why do we care about the remainder in the Taylor formula? Well, because that's what we need to prove a change of variable formula. And this is what's done in the paper with Perkovsky. What we show is that if we have a path S, which has for which this sequence of functions converges, so a path which has local time of order P in this sense, along some sequence of partitions pi, then if we compute the following compensated Riemann sum, so I'm going to take the increments of the function f along this partition, and I'm going to do a Taylor expansion of order p minus 1 of each increment. So I'm going to do this calculation for each increment of s of f of s along the partition of times. So each increment is going to give me a term like this, plus a remainder. And, well, the existence of local time means that the remainder will converge exactly to a term like this. And so because the left-hand side is just the sum of the increments, it will converge to the increment of f of s. So it means that what's in the middle, so this the limit of Taylor expansions should also converge. So this is what we call a compensated Riemann sum. So if you have p equals 2, this is just a Riemann sum. So it's a Riemann sum where you include further terms of the Taylor expansion up to order p minus 1. If p is a fraction, then p is not an integer, then this will be the integer part of p minus 1. And so you get this Ito type formula, in fact, the Tanaka type formula, where you have f of st minus f of s0. So you compute a smooth function along the irregular path. But the smoothness is linked to the irregularity. So S has roughness index P, and F is of CP by minus 1. And then you see that you have an Ito-type formula. So the first term is an integral, and this integral is a compensated left, a limit of compensated left Riemann sums. And then you have a remainder term, which is an integral of the last derivative, fp, with respect to the local time of order p. So you can think of it as a high order Tanaka formula. So this really shows why we're interested in this Taylor expansion and the remainder, and why this is the correct definition, because if you define it like this, then this is exactly what shows up in the discrete approximations, and it will converge to the remainder term in the Tanaka form. Okay, so this makes it a bit less ad hoc, if you want. Okay, anyway, I'm not going to use the change of variable formula in what follows in this talk, but this just shows you where this local time comes from. It's not an ad hoc quantity. What I'm more interested in is the relation between this local time and level crossings at level 0. But maybe this is a good time to make a break. Yeah? Or should
yes.
I? Okay, so let's take a break now, and then
Yes.
Any questions about this first part? So it's a little bit technical, but now I think what I will show you now will justify expose this definition. So as you can see, what this definition does, it takes a time grid, a partition pi n, time steps tj plus 1, and then it does the following. Look at the formula. What it does is this. It measures something related to the pth order variation. So it looks at the increment to the power p minus 1 only when the signal is around x. Okay, only when the signal is in this interval around x. Okay, so and then it sums this, and when the step size goes to 0, it's really the interval shrinks, so it's really at x. So it looks at the contribution to the pth order variation when you are around x. Okay. So now we're going to see that this quantity is directly linked to the number of level crossings, up crossings or down crossings. So this is the following lemma, which, okay, you can find the proof. I'm going to give you the proof, but you can find it in more detail in the paper with Perkovsky. But I think it's not new. It's you find different versions of this for semi-martingales, for example, in El Karoui, 1978. But the proofs were probabilistic. They involved semi-martingales, but in fact, there's nothing probabilistic. It's just a pathwise proof. So what's the statement? So now we're going to look at a specific partition just to fix ideas. So it's again the Lebesgue partition. So you look at the sequence of hitting times of levels distanced by delta n. And so we're going to look at the level x. So for each n, x is inside of some dyadic interval. So we call this interval ink of x. Okay, so it's an dyadic interval containing x. And we're going to look at the number of up crossings or down crossings of this interval by the signal s. So what is up crossing? It means s goes from A to B. That's up crossing, or down crossing, s goes from B to A. So this is exactly the concept that we used yesterday. What we call delta excursion is you have to go from 0 to delta or from delta to 0. So this is an up crossing and a down crossing. So here we count the number of up crossing and down crossing of some interval AB. up to time t. Then the statement is that this discrete quantity, discrete local time L pi n t that we define, again, this thing here, L pi n t is exactly, has a relation with these up crossings and down crossings. And the relation is shown here. It's LT is some expression involving the level x times the number of up crossings plus some other expression involving x times the down crossings, plus a correction which will go to 0 as 2 to the minus n p minus 1. Okay, so this is really what will help us, because we're interested in the up crossings or down crossings, because these are the delta excursions. And it shows that the local time of order p, as we defined it here, is gives you an estimate of these. Okay, where does this relation come from? Well, it comes from the expression of L pi n. So L pi n, remember, is defined as the sum. Okay, so this sum involves these indicators of these intervals. So every time you cross one of these intervals, you get a contribution, which is shown here, which is the end of the interval minus x to the power p minus 1. So if you fix x and then you look at how many times you cross these, and for each up crossing or down crossing, you will get a term like this. And the term you get, so you can see that there's a time ordering here. You look at the value at the end of the interval minus x. So depending on whether you up cross or down cross, the end of the interval will be a or b. So this will change the expression here. It will be a minus x or b minus x, but you will get one of the two, and then the number of terms will be the up and down crossing. So that's exactly the proof. It says, okay, well, if you have this indicator that is not 0, so if one of these terms is non-zero, it means that either you enter this interval through this point or this point, okay? So, and then you exit it at some point through the other one. So it means that if the indicator is not 0, it means that you have either S is equal to this endpoint of the dyadic interval, either at the beginning or at the end. So this is an up crossing, or you have the opposite. You have a down crossing. So it means that you start from the higher value, go to the lower value. So to cross an interval, you either cross it up or down. So in the first case, as I said, the term, when you do up crossing, so remember the term in this sum is the last, is the value of S at the end of the interval. So if you do up crossing, the end of the interval is the higher value. So you get a contribution which is equal to this. In the second case, you get a contribution that is, the x but minus the initial value, but then you have a sign, because you have b minus x or x minus b, but then you have a sign. Okay, so so if you sum these, you just obtain that these will be the up crossings give you these terms and the down crossings give you this term. And then you have the other terms. So these are terms where you do not cross with this interval, and you can show that this is of order the 2 to the minus n p minus 1. Okay, and now so this expression you have both up and down crossings, but the up and down crossings of I differ by at most one. Why? Because eventually you have to get out of the interval. So you cannot, you can have 3 down crossings and 1 up crossing, because otherwise it means you're still in the interval and then you stay there. So this leads to the formula here. So we will mostly use, the first one, or we will use it with down crossing. So it means that if I know something about the local time over the P, I also know the down crossings or up crossings up to this formula here. Okay, so why is this interesting? Well, we're going to show that now this formula will allow us to analyze the properties of these trading strategies, the mean reversion strategies, as delta goes to 0, and relates their properties to the local time of the path of the signal. So the limit delta goes to 0 correspond to small trading thresholds, but for irregular signals, small trading threshold means that you're going to cross it very frequently because you're going to have an oscillating behavior at 0 if there is a non-zero observation intensity at 0. So this also corresponds to the high frequency asymptotics of the strategy. So rather than fixing the frequency, saying I want to trade every second, that's not what people do. You fix the threshold of trading, and then you will have a natural or effective trading frequency, which is associated with delta. But we're going to show that this effective trading frequency, you cannot fix it. It will depend on the roughness of the signal. The rougher the signal, the higher the effective trading frequency for a given delta. And we're going to estimate that precisely. And then we're going to estimate the realized profit, because every time you trade, you make a profit delta. So delta times d delta is the realized profit. And we're going to see how that behaves as delta goes to 0. And both of these things, as we will see, will depend on the roughness index of the path, which we call P. Okay, how does that work? Well, so again, let me recall just what I just showed you. So I just showed you a formula relating the local time and the up and down crossings, but this is for a general interval A, In fact, we only care about the interval near 0. So I'm going to apply this now to the interval 0 delta. Well, delta is our threshold, the trading threshold. So I'm going to index delta by n. So delta n is 2 to the minus n. You can think of it as 2 to the minus n, but any delta go to 0 works here. So what we showed is that the local time of order P at a level x is, so now I'm going to take x inside this interval 0 delta n. It's a small level. It's going to be of this type. It's going to be number of down crossings. So these are the delta excursions to the power p minus times x to the power p minus 1 plus number of up crossings times delta n minus xp minus 1. So in this case, the interval is AB is 0 delta. So here we get x minus 0, and here we get delta n minus x. So again, because the up and down crossings differ by at most 1, I can absorb the up crossing term in here, and both terms here will be of order. So x is between 0 and delta. So both of these expressions are delta to the power p minus 1 plus a lower order term, or a term of at most order p minus 1 in delta. So it means that the local time of order p at 0 of our signal, that's the left-hand side, will be equal to the number of down crossings. So this is exactly the number of delta excursions, because every time you cross down from delta to 0, you trade once, times delta to the power p minus 1. Okay, so so this is very interesting because it's so, and then plus a term that goes to 0. So it means that the limit of this term is exactly the local time of order p. Okay, so this is the formula I'm going to use now. It says that number of delta excursions times delta to the power p minus 1, Well, P is the roughness index of the path. This thing converges to the local time of order P, which we assume to be strictly positive. There's non-zero local time of order P because P has p order S has p order variation. Roughness index is P, so this is non-degenerate. So this gives us the asymptotic of number of delta excursions as delta goes to 0. Okay, so this is exactly what we need because we want the asymptotics of d delta, number of delta excursions, and realized profit, which is delta times d delta. Well, this tells us exactly what's going to happen, and it's going to depend on the roughness index of the path. Okay. So here is the statement. So I'm just going to use this formula and reformulate it in terms of the quantity we're interested in. So this is the result we're going to use. Okay. So I take a continuous path which has roughness index P, and a little bit more. It has strictly positive local time of order P, 0. And then I take a threshold delta n which shrinks to 0. Then, well, the statement is the following. Depending on the roughness index P, we're going to have very different behaviors. So if P is strictly smaller than 2, so it means that so remember 2 corresponds to Brownian motion, the roughness of Brownian motion. So P strictly smaller than 2 means that it's a bit smoother than Brownian motion. So 1 will mean it's a path with finite variation. It's really much smoother. But in between 1 and 2 means it may not have finite variation, maybe, but it's smoother than Brownian motion. In this case, the realized profit of the strategy, which is delta times d delta, number of transactions times delta, goes to 0 as delta goes to 0. Okay. So in this case, it is certainly not optimal to take very small thresholds because you drive the profit to 0. In this case, the optimal threshold will be a non-zero value, and high frequency trading on this strategy is not optimal. Second case, if P is strictly larger than 2, it means that the signal is strictly rougher than Brownian motion. In this case, you can show that delta times d delta goes to infinity. Why? Because you can see that if P is strictly bigger than 2, then the d delta times a power of delta higher than 1 is going to have a limit. So if you take here a 1, then you go to infinity. So this means that, and in fact, more precisely, you have that the number of transactions with the threshold delta will behave like the local time of order P divided by delta to the power P minus 1. So, for example, if P is equal to 2.5, then you can see that this is going to be square root of delta. So it means that the number of transactions increases like 1 over square root of delta when you shrink the threshold. And in that case, the realized profit goes to infinity. So it means that in this case, if you really think that your signal is rougher than Brownian motion, then you should trade at the highest frequency possible and with the lowest threshold possible. And this is more or less what happens in the high frequency trading versions of these strategies. A lot of high frequency trading firms use these mean reversion strategies with the highest frequency they can. You know, it's only a technological limit to what they can do. And this statement says, well, this is optimal if your signal is rougher than Brownian motion. Third case is if P equals 2. If P equals 2, then it means that your signal has the texture of Brownian motion. It's a semi-martingale or something like that. Then in this case, you have that the realized profit when the threshold becomes smaller, converges exactly to the local time of order 2. And the local time of order 2 is, as I will show you, it's the same thing as what's called semi-Martingale local time. Okay, so it's not a different notion. So this is interesting because it shows that, well, this doesn't show you whether this is optimal to take delta equals to 0, because you need to look at how this behaves as a function of delta when it goes away from 0. But it shows that if you take at very high frequency, you have a non-zero residual profit, and it's exactly equal to the local time at 0 of your signal. And interestingly, I think it gives a new, interesting financial interpretation of the local time at 0. It shows that the local time at 0 is, in fact, can be thought of as as the the realized profit of a high frequency trading strategy using that signal. So it's a very concrete financial interpretation, which I think is new. I haven't seen this before in the literature. So this result shows that really it depends on the crop roughness of the path, whether you should use small thresholds or large thresholds, whether you should do high frequency trading with this strategy or not, depends on the crop roughness of the path. In summary, unless the path is rougher than a diffusion, it is not optimal to take very small thresholds or trade at high frequency, even if you can. So I think that's an interesting result, which is qualitative. And again, it doesn't make any specific assumption on the stochastic process by generating S. This result is valid for a single path. But now I'm going to apply this result to various classes of stochastic processes for which we know something about the roughness index of the paths. And of course, then we can apply these results almost surely to their paths. Okay, but again, the statement and the proof of this result, this is the proof is based on this level crossing identity, has strictly no probabilistic assumption, so it's applicable to anything you want. Any question about this? Okay, so now I'm going to show how this applies to paths of different stochastic processes, and then how it applies to high frequency data, and what values of roughness index do we find in these examples. Okay, so the first class of examples is a very important class, which has been used almost all the time in finance. It's semi-martingales. So Brownian motion is a special case. So think of a semi-martingale as a signal plus noise, where the signal is bounded variation and the noise is a martingale. This is a well-known result that the roughness index of such a process is 2, and any semi-martingale has local time of order p equals 2, which is defined classically in this way. It can be defined in this way. It's you look at how much the process S, the path of S, accumulates quadratic variation. So here the pth order variation is p equals 2, is just a quadratic variation of the signal. And so you look at how much quadratic variation you accumulate when you're near 0, and that's the local time of order 2. And up to a constant 2, it's the same as what's called in the literature the semi-martingale local time of S. So here we have 1/4, but in the definition of semi-martingale local time, you have 1/2. But that's the only difference. So up to a constant 2 is the same. And in fact, these quantities and the relation in the same martingale case between this local time and level crossings was studied by El Kawi in 1978 for other reasons. I'm not sure for what reason, but she completely characterized the relation between the local time and this quantity, which we call the delta t, the number of level crossings delta, so delta excursions. It's not called like that in the paper, but it's the same quantity. I rewrite her result in the notations. So what she showed is that if you take a semi-martingale whose characteristics M and A are integrable for some in some LQ, then in fact it's even stronger than what we said before. What we stated here is that for a fixed time you have this convergence, but in fact El Kawi showed that if you look at the number of delta excursions times delta, this function as a function of time, it's uniformly approximated at all times by the local time of order 2 as delta goes to 0. So that's the statement. If you take this local time order 2 and you use so the first expression is the realized profit of the strategy, and the second is the local time over 2. In fact, this approximates that uniformly over time. Any horizon works in LQ. Okay, so not only it goes to 0, but its Qth moment also goes to 0. So okay, so it's a very nice result. So it shows that this is indeed the correct interpretation. The local time of order 2, or the semi-martingale local time, can be thought of as the realized profit of a high-frequency trading strategy of a mean reversion strategy with the threshold going to 0. Okay, so this I think is a nice thing in itself because it gives a financial interpretation of local time, which is directly shows the financial significance of the concept of local time, because it corresponds to the profit of a certain strategy, which is explicit. Now, another example which gives us a different level of roughness is fractional Brownian motion. So what is fractional Brownian motion? It's a Gaussian process indexed by a parameter h called the Hurst index between 0 and 1. It's a Gaussian process with mean 0 and a certain covariance function here, which shows that it can exhibit long-range dependence if h is bigger than 1/2. And well, we're not interested in this talk in the Gaussian properties of B, but in the roughness of B. So what do we know about the sample paths of BH? Well, we know that BH is almost surely Holder continuous for every index smaller than H strictly. So H is the upper Holder index of BH. For H equals 1/2, we have Brownian motion, but we know that it's 1/2 minus epsilon Holder continuous for every epsilon. So this is a similar statement. And in fact, it has almost surely roughness index 1/H. So its pth order variation for P equals 1/H is non-zero, and it's proportional to time. Okay. So in the case of Brownian motion, again, this is well known, and this constant is 1. But this is also true for any fractional Brownian motion. So the roughness index is 1/H. Okay, and so here I'm just giving a very quick overview. But if you're more interested, there's a very nice video lectures of Elisa Alosh, who left now, and she gives a nice overview of Brownian motion of fractional Brownian motion and applications in finance, which she has been working on a lot. And in general, in Barcelona, there's no shortage of experts on this topic. Yes?
Sorry, Rama, yeah, there's a question in the chat that maybe is interesting now. It says, for illustration, can you give us an example of such process exhibiting roughness outside finance in physics, for example?
Oh, is that the question? Because I don't see the chat.
In the chat, yes.
I don't see the chat. So yes, so in fact, fractional Brownian motion was introduced in the 60s by Mandelbrot and Van Ness in the context of hydrology, not in finance. It was introduced first in the context of hydrology. In fact, they were interested in, they were looking at time series of flood in the Nile River. And the Nile River, because of the Egyptian civilization, there are statistics on the floods in the Nile going back thousands of years. So it's probably one of the longest time series you have in hydrology. And so they were able to look at this this data, and they proposed this fractional Brownian motion as a model for this hydrological time series. But subsequently, one of the first applications after this was Mandelbrot himself used this to build a model for economic time series. So yeah, from the early literature, it was used as a model for economic time series. Now, in the context of these trading strategies, actually, fractional Brownian motion is used a lot to model trading signals, especially in pairs trading. So I've seen that a lot. So I'm going to show you now a model that can be used to build from fractional Brownian motion to model these mean reverting signals. So now this is an interesting example because you have this parameter h, which goes from 0 to 1. And this result says that by changing h, you can get various levels of roughness. So P is equal to 1 over h, the roughness index is 1 over h. So if you range h from 0 to 1, you're going to range the roughness index from 1 to infinity. And in fact, you can get any level of roughness between any roughness index greater than 1 by choosing h appropriately. And here are some simulations of fractional Brownian motion for different levels of h. You can see even with the eye that the roughness is changing when you change h. So in this case, roughness index is 1 over h. So higher h means smoother paths, a lower roughness index. So h equals 0.9 will correspond to a roughness index close to 1.1. And this is really close to it's very close to a bounded variation path. And h equals 0.5 is Brownian motion. So this is a typical roughness of a Brownian motion. And you can see that for h smaller than 1/2, you have a roughness index which is larger than 2. You can see that the path looks more rough than a Brownian motion. And for h getting close to 0, you can get arbitrarily rough. It's really, it gets very zigzaggy. Okay, so this is an example where you can see all ranges of roughness. So if the theorem that I showed you earlier is correct, and if it applies to ranges of frequencies that are realistic, we should be able to see all the kinds of behavior predicted in the theorem when we use a simulation of a fractional Brownian motion with different h. Now, but to apply the result that I showed you earlier, we need more than just a roughness index. We need to show that the process has a local time at 0. Well, it turns out that this is the case for fractional Brownian motion. So fractional Brownian motion almost surely has a continuous local time of order p equals 1 over h, same index, at 0, along the sequence of partitions, let's say the uniform partition or the Levet partition, both have been shown in the literature. And Well, in this case, okay, so I didn't comment on this before, but I defined in the first part the occupation density, and in the second part of the talk, I defined the local time of order P. For fractional Brownian motion, they are proportional. They are the same up to a constant. Okay, it's the same for Brownian motion because the pth order variation is proportional to t. So whether you look at occupation time or the pth order variation, you're looking at the same thing up to a constant. Okay, so in this case, the occupation density is proportional to the local time of order 1 over h, and the proportionality constant is shown here. Okay. In the literature on fractional Brownian motion, what is discussed mostly is the occupation density. For example, this book by Oxendal and Biagini and so on, they discuss the occupation density, whereas for stochastic calculus, as I showed you in the Tanaka formula, what is relevant is the local time of order p, but for fractional Brownian motion, they're the same. Okay, so this is a known result from the literature that local time is strictly positive and in fact proportional to t. So this means that our result applies, and the result states that. So remember, the result states that for you have this. Asymptotics, delta to the p minus 1 times d delta has a limit, and in this case p is equal to 1 over h, so delta to the p minus 1 is delta to the 1 minus h over h. Okay, so the statement is that for any fractional Brownian motion with Hurst index h, if your signal is fractional Brownian motion, then the number of level crossings times delta to the 1 minus h over h converges to the local time of order 1 over h, which is equal to the occupation density times the constant. So it means that the number of level crossings, or so the number of transactions when your signal is fractional Brownian motion, will behave like a constant, which is, you know exactly what this constant is, in fact, divided by delta to the 1 minus h over h. So what does that mean? It means that up to a constant, which is explicit, the number of transactions for your strategy will be delta to the power 1 minus 1 over h, and the realized profit will be of order delta to the 2 minus 1 over h, because it's, the realized profit is delta times this. Okay, and now we can see that depending on h, well, this can go to 0 or infinity, or to a constant. So it's going to be very dependent on the smoothness of the path. For some, for h larger than 1/2, this is going to go to infinity. For h smaller than 1/2, it's going to go to 0. And for h equals 1/2, you don't know. You have to look at, but then we have another result which showed us that it has a non-zero limit. And the number of transactions for will always go to infinity, but that doesn't mean they're profitable, because as we saw, the realized profit can either shrink to 0 or go to infinity. Okay, so that's the statement for fractional Brownian motion. Now, fractional Brownian motion itself directly is rarely used as a good model for a signal, because the signals we're interested in are mean reverting signals. So fractional Brownian motion is not a mean reverting process, it's a non-stationary process, in fact. So a model that is more often used in finance is the fractional Ornstein-Uhlenbeck process, which is the solution of a linear stochastic differential equation driven by fractional Brownian motion. So it's the same form as a fractional, as a Ornstein-Uhlenbeck, except that you replace the Wiener process by fractional Brownian motion with Hurst index H. And this is a linear equation whose the solution is explicit. This is the solution. So you have an initial condition that you forget exponentially. And then this part, the stationary part, is shown here. It's really an integral of a deterministic function, exponential with respect to the fractional Brownian motion. So these fractional OU processes are used in many cases in finance to model volatility in particular. And this defines an ergodic Gaussian process whose the covariance and mean are explicitly computable, so I'm not going to do it here, and whose roughness properties are similar to fractional Brownian motion. So it has the same roughness index as the driving fractional Brownian motion. That's the only thing we're interested in here. So if you, I'm not going to say more about the fractional Ornstein-Uhlenbeck, but it says a very nice paper by Kerry Dito et al., which studies this, and again, it's something that you find a lot in papers on rough volatility these days. So that's why it's an interesting example of this. So what I'm going to show you now is I'm going to simulate a sample paths of a fractional Ornstein-Uhlenbeck process with different H. And we're going to stimulate them over 1 day at a frequency which is 1 second. So this is a realistic simulation for intraday financial data, because it is realistic for high frequency trading to trade over a frequency of 1 second. In fact, you can trade at higher frequencies, but 1 second is certainly realistic. And so we're going to look at if you trade, if you're able to trade at the frequency of 1 second, and if the signal has roughness H, then should you trade, in fact, at the highest frequency you can, or should you trade at a lower frequency with a higher threshold delta? That's what we want to see. So here is the results of the simulation for this fractional Ornstein-Uhlenbeck process. So I show you the results for 3 different levels of H. So H, in the middle, you have H equals 0.5. This is Brownian motion. H equals 0.3 is rougher than Brownian motion. H equals 0.7 is smoother than Brownian motion. So what are we showing here? We're showing d delta, the number of transactions, which is what we call the effective trading frequency. So it's a double logarithmic plot. So you see the log of delta and the log of the delta here. So these plots, what do they show? They show you the effective trading frequency. It shows you that if the signal is this, and if I choose the given level delta, like for example here, I choose 10 to the minus 2 for delta, then the strategy will make me trade at this frequency. Okay, so the frequency, I cannot choose it freely. If I choose the level, I choose the frequency. And so this graph shows the correspondence between the threshold and the frequency of trading in this strategy. And the prediction of the asymptotic formula is that this graph, as delta goes to 0, so as we go to the left, it should behave as delta to the power h minus 1 over h. And this function, delta to the h minus 1 over h, is the orange line with the that is plotted on each plot. So the blue is the simulation, and the orange is the asymptotic behavior according to the formula I showed you earlier. So remember, this asymptotic behavior is only valid when delta goes to 0. So we want to see what delta goes to 0 means. Is it 1 day? Is it 1 second? Is it 1 minute? And what you see is that, well, actually it works quite well. So the smallest delta here is 1 second, and you can see that you do see the asymptotic behavior. So the blue and the orange dotted line, they do coincide in the three cases. So it means that these asymptotics are not ridiculous. They actually work for intraday frequencies of order of a minute or a second, certainly for a second, and even for a few minutes, they are correct. So they give a correct description of the behavior of high frequency behavior of these strategies when you look at small thresholds. But if you go far from this, for example, if you look at a really big threshold, then okay, then this is not the correct description, but for the asymptotics are correct. So this shows that, this asymptotics is useful and it works for intraday frequencies. And so it does describe how the strategy behaves when delta goes to 0. Okay. Now, these are simulations. So of course, here we're just checking that the theorem works because we, hopefully theorems are true. And we're just checking that the asymptotics works in a certain range. But what happens with real data? So that's what I'm going to show now. So I showed you yesterday 2 examples of pairs trading signals constructed from pairs of stocks. So we take two pairs of stocks, look for a linear combination of these 2 stocks, which leads to a stationary mean reverting process, and that's what we call the pairs trading signal. So the first example I showed you yesterday was Coca-Pepsi. So Coca-Pepsi is very well known as an application of pairs trading. How does it behave in terms of roughness? Well, here's the graph. It's the same graph as the simulation before, but now it's for Coca-Pepsi pairs trading signal. Again, I plot on the horizontal axis the threshold. So here it's the threshold divided by the standard deviation of the signal. So 1 means 1 standard deviation. Most pair trading strategies operate here. They take a threshold of 1 standard deviation, but we vary the threshold. And so the blue shows you the number of transactions in this strategy when you vary the threshold. And what we try to see is what's the best approximation in log-log plot with a straight line, which will then enable us to give an estimate of P, the roughness index. In this example, if you, for example, fit the blue line in the left with this dotted orange line, there's more than one way to fit it, but if you get the best fit with a straight line gives you this orange line, which corresponds to P equals 1.85. So 1.85 is quite close to 2. And if you take 2 gives you, so the diffusion case gives you the green line here. So it means that in this case, we're close to a diffusive behavior. It's slightly smoother, but I mean, it's not clear with these estimates whether you have a very precise estimate of P. But yeah, so you have close to diffusive behavior. And if you look at the realized profit, which is delta times d delta, well, then you see this profile here. This is interesting. It means that, okay, so as we expect for a diffusive type behavior, as delta goes to 0, the profit doesn't shrink to 0. It converges to a non-zero value. Okay, so this is given by the local time of order 2 in the same Martingale case, but there's no reason for this to be optimal. And in fact, what we see is that if you look at the realized profit, it has a peak as a function of the threshold, which is away from 0. Okay, so if P is larger than 2, then this should go to infinity as delta shrinks. But if P is smaller than 2, which is the case here, then we expect the optimum to be away from 0, and this is the case. So this gives interesting information. It says that, oh, with this signal, it is not optimal to take the highest frequency you can, or the smallest threshold you can. In fact, there is an optimal threshold, which in this case is around it's around 2 standard deviations. So it's not very small. Okay. So that's interesting. So it shows that, you know, this asymptotics works, and the asymptotics tells us also that you shouldn't take too small a threshold. It's not the case that because you can trade at high frequency that you should be taking the small threshold. In fact, you should be operating here, which is around 2 standard deviations, and 2 standard deviations is corresponds to this frequency here. So that's an interesting example. Another example is the other one I showed you yesterday. I showed you the a pair, which was 2 exchange traded funds. And we look at the, so this is SH and SDS and 2 colors here, and we do a regression of one on the other, and we find this weight here, 0.67. So if you combine SH with 0.67 SDS, then you get this signal here, which is the trading signal. So question is, what's the roughness of the signal, and what is the result in terms of the threshold? What threshold do we choose? The smallest possible, or something away from 0? So here is the result. So in this case, it's smoother than the Coca-Pepsi signal. If you do the same regression, if you do the same log plot, and you try to fit the behavior for small thresholds with the straight line, you get a straight line which corresponds to p equals 1.2. So p equals 1.2. So remember the slope here is p minus 1. So it means the slope here is 0.2. It's very flat. In logarithmic plot, it's very flat. So it's and if you look at the realized profit, well, in this case, p is strictly smaller than 2. So the prediction is that as delta shrinks to 0, the realized profit should shrink, and in fact it does. And you see that it's optimal to take here a threshold, which is in this case close to 1. It's 1 standard deviation. So again, this is delta divided by standard deviation. So it shows that, again, you may be able to trade at high frequency, take low thresholds, but it's not optimal to take low thresholds because we're in the regime smoother than Brownian motion. So it is not optimal to do that. You should choose a threshold which is around 1 standard deviation. And this is in fact what people do a lot, but not because they did this analysis for other reasons, but here it shows that the smoothest analysis but supports this conclusion. And note that here, so often in the pairs trading literature, they use the Ornstein-Uhlenbeck as a model, and then they calculate somehow the optimal threshold delta. But here, there's no probabilistic model. We just analyze the smoothness of the path with the roughness index. So this is a purely pathwise analysis. No assumption on the exact process for generating the signal. So I think that's interesting. And it's interesting that you arrive at a similar conclusion, but without making any of those assumptions. It has nothing to do with the Markov property or whatever, the Gaussian nature of the signal. It has everything to do with the smoothness index of the path. Okay, so all these examples I showed were based on the strategy, which was the upside strategy. So you short when the signal goes above delta, and then you sell when it reaches 0 again. It's a one-sided strategy. What about the downside? What about a two-sided strategy? Does it change? Well, it doesn't. So here is just to give one example. I mean, it could be different. There's no reason for up excursions and down excursion to be similar. They could be different, but it turns out that for these examples, they're not. So this is the example for Coca-Pepsi pairs trading signal. So here we do the analysis separately for up excursions and down excursions, shown here in blue and red. And in fact, they have a very similar behavior in terms of number of level crossings and the realized profit if you trade only the up excursions or the down excursions. So they're slightly different, but when delta goes to 0, they behave similarly, because when delta goes to 0, basically it's very difficult when you have a delta which is smaller than 0, you have an interval plus or minus delta around 0. It's very difficult for the signal to oscillate without crossing on both sides. If delta is very small, then if you cross, if you have some volatility, you will cross on both sides. So it's the number of up and down crossings will be very similar. But if delta is large, that's not true, because you can go up and not go down. So you can see that for delta large, the two curves are different, and that should be different. I mean, these signals are not symmetric perfectly, but for small delta they are. So the high frequency behavior is the same for up and down crossings. And you can do the same for other signal. I'm not going to show the graphs, but they have a similar behavior.
Maybe it's time to finish. Maybe
I'm done. So
okay.
I am.
Take your time, but take your time.
Yeah.
No, say. This is references.
Yes, some references to.
There is still a question. I